And yeah, so the next presentation is coming from Juan Ignacio Martinez, who is a business analyst at Becquerel Institute. And he's going to talk about the potential for advanced solar module applications. Juan, the floor is yours.
Thank you, Shavran. I'll share my screen. Okay, thank you all very much for joining this morning. My name is Juan Ignacio Martinez. I'm part of Becquerel Institute Spain, and I'm here to talk to you about the potential for advanced solar module applications, which is about the work that we conducted for the Seamless PV European project. A little bit about Becquerel Institute. We are a strategy consulting company that works with project developers, manufacturers, associations, and researchers in everything related to solar. Both in consultancy missions and also in research projects. We have offices in Belgium, France, Spain, and recently opened one in Italy. And about the Seamless PV project, it's a European PV project, a Horizon Europe project, in order to develop advanced, flexible, automated PV manufacturing and to pilot and demo these modules or these applications in real cases. So in buildings, vehicles, infrastructure, and agriculture. This presentation is divided into 4 sections. In the first one, we'll look into what is integrated PV. And the second one, we'll look into the methodology and process we follow for our estimation. Then we'll go over the results, and finally, some general remarks. First, the context. So integrated PV allows you to seamlessly integrate solar into buildings and infrastructure without sacrificing aesthetics. That's the main idea, and it has dual functionality. It has aesthetics and synergies with other sectors. And there are multiple applications that we can take a look into, but we will focus on the ones we studied in Seamless PV, which are first BIPV, and that includes roof, facade, and also external device applications, but we will focus more on roof and facades. And here you have skylights, shingles, curtain wall, raised facades, and then infrastructure integrated PV or IIPV, where we have PV noise barriers or commercial and residential carports. AgriPV, like we just saw in the last presentation, we have many different forms of it, like in PV greenhouses, elevated PV with tracking, vertical PV. And finally, vehicle integrated PV, and we looked into the integrations for this into passenger vehicles, buses, and trucks. So for the methodology we used. Well, first, we only focused on Europe, particularly in the EU, the UK, and Switzerland from the years 2024 to 2050. And this is the general process that we follow, which is a multi-step process that systematically narrows down the potential that we estimate based on a series of exclusion factors, and is divided into 2 main sections: the technical potential and the specific market potential. The technical potential is the potential for all PV for that surface. So without making a distinction if the module to be installed is integrated or not. And the specific market potential makes that distinction, considers the specific characteristics of the module to only allow for the IPV application to be considered. And then we also transform on the last steps. We transform this potential, which started as surface area, into capacity via a series of assumptions. We do not take into account the SOM, the serviceable obtainable market, that was not in the scope of Seamless. We stay up to the serviceable addressable market, which is the main market for the entire segment as a whole, not the individual applications. So the parameters and hypotheses that we use for the technical and the specific market potentials for each IPV segment are different and are adapted to the characteristics of each one. Furthermore, on the last step, the serviceable addressable market, we use the diffusion of innovations model, or the S-curve model, which explains how innovations spread over time, with adoption starting slow, accelerating after takeoff, and plateauing when the innovation approaches market saturation. So now onto the results. We'll start with BIPV. And for this, we had two scenarios. The renovation web scenario, which considers a major increase in building renovations, and the non-renovation web scenario, which is a business as usual type of a scenario. And it's important to note that BIPV can only be installed when you have a new construction or a renovation. So that's the key characteristic of the integrated solution that we consider when moving from the technical potential to the specific market potential that I mentioned before. So as for the technical potential, we see that starting from the gross technical potential in 2024, we extrapolate based on the number of renovations and constructions to 2050. And then after applying a series of factors to account for architectural limitations and low irradiation areas, we get around 12% of our original capacity, or original potential, with facades comprising over 2/3 of this gross technical potential. Then moving on to the total addressable market, so only the integrated solution, we see another reduction of 4,400 square kilometers. And then finally, for the SAM, we see a big reduction from the TAM of over 90% of it, because we use the S-curve model to limit how the market would grow. So it put a ceiling onto it, pretty much. And after converting that to capacity, via considering the surface type, the cell technology, the semi-transparency levels, making assumptions on that, we get that we expect a potential of almost 140 gigawatts in the renovation web scenario and over 90 gigawatts in the non-renovation web scenario, with roof representing most of the potential in both cases. So here you can see it clearly. Although this does not really have the shape of an S-curve, this just means that the market will continue to grow. It's not approaching saturation, and it will reach almost 140 gigawatts by 2050 in terms of potential. So it has a massive potential. Roof dominates the potential, and an increase in renovation activity and better adoption by the construction sectors are key into unlocking a large part of the BIPV potential. And like I previously said, BIPV installations will not plateau by 2050. The market size will continue to keep increasing beyond that. So then we have PV carports, and we have two types, commercial and residential carports, and two scenarios, high and low scenario representing just regulatory support and adoption rates. The methodology for both commercial and residential is similar. The only thing that changes is how we calculate the gross technical and the realistic technical potential. So in the case of commercial carports, we look at the carport area available in Europe. And in the case of residential carports, we based it on the number of single-family housings in Europe and making assumptions on the size of a parking and the number of parkings that they would have, that single-family housing would have. So the trend for both commercial and residential carports is similar, and the technical potential for both is quite large. The main difference we see it's when moving from the realistic technical potential to the economic technical potential, which is about the radiation that it receives. And it's just because commercial carports are usually set up in open areas, so are less affected by obstacles and other shading objects. But when we move on to the specific market potential, we apply the S-curve model. Commercial carports dominate the segment and are projected to surpass 100 gigawatts of market potential if they have the right regulatory support. Commercial policy support will play a key role in expanding the potential of this application, particularly for commercial applications. Residential applications will remain a niche. They are not expected to grow as much as commercial. And the synergy with EV charging infrastructure further supports PV carports as a significant energy asset. Then we have PV noise barriers with two scenarios, also based on regulatory support. For the technical potential, we take it's based on the available area alongside highways and railways in Europe, and the total addressable market is based on, out of that area along highways and railways, what is actually noise barriers. And the sum is what can actually be built onto PV noise barriers. So as we see, according to a study conducted by the JRC last year, which looked into the potential of linear PV alongside major European railways and highways, the potential is massive with over 400 gigawatts of capacity, but noise barriers only represent a small part of it and are constrained by design and high cost, which limit their adoption. And the potential for PV&B is not as high as for the other applications. We see here that even in the highest scenario, it's not expected to reach even half a gigawatt of capacity, of cumulative capacity by 2050. But it will continue to grow steadily, driven by regulation and infrastructure expansion. It is, as of now, it's highly concentrated in only a number of countries like Switzerland, Germany, and the Netherlands. So we still need to see whether other countries would adopt this technology. Then on agriPV, we have three scenarios: loose, medium, and strict regulation scenarios, which I will not go much into detail about because we don't have much time. But in general, the potential for agriPV is absolutely massive, with over 75 million hectares remaining available even after subtracting all the protected land areas, high nature areas, biodiversity zones, etc. It still holds a massive technical potential. And when we look and we convert that into capacity and look it through the lens of the serviceable addressable market, it's absolutely massive, with over 3 terawatts in the highest scenario and over 1 terawatt in the lowest scenario. So it has by far the largest potential amongst IPV applications, but it is highly sensitive to regulation. And we are expecting growth to accelerate past 2035, reflecting increasing policy support, maturing technology, and stronger alignment with agricultural practices. Then we have vehicle integrated PV. And for this, we consider 4 vehicle types: light vehicles, light commercial, heavy commercial, and buses, and also 2 scenarios. The high scenario considers a faster increase in the EV share in Europe and a faster adoption rate of BIPV. And the lowest scenario, it's more moderate and has a slower adoption rate. So for the technical potential, we have that rapid EV adoption drives BIPV's technical potential, with technology advances enabling greater use of vehicle surfaces for solar integration. The roof and upper body panels offer the most suitable areas for BIPV, while complex geometries on the side or on the side of the car or in some parts under it limit its potential and are also affected by significant shading. Integration feasibility and cost remain the key limiting factors of this application. And it has a decent potential when we look at it into a specific market potential with between 7 and 17 gigawatts by 2050. But we do not expect this technology to take off anytime before 2040. Early adoption will start slow due to cost, integration complexity, and a limited number of product availability. But it will expand rapidly with the electrification of transport as well. Innovations in lightweight modules, flexible materials, and integrated vehicle design will be key to unlocking large-scale adoption for this. And though still emerging, BIPV represents a long-term growth opportunity aligned with Europe's mobility decarbonization strategies. And as a bonus, I have lightweight PV, which has a unique value that you can exploit the surfaces that we have just discussed, like buildings or vehicles, but without having to integrate the module onto the surface. So lightweight modules are generally over 50% lighter than a regular module and come in different geometries and shapes, and some are even flexible. So they are very versatile for all sorts of surfaces. We looked at the potential for them, but and although you can have them on agriPV, you can have them on vehicles, we focused on buildings since that represents the the more interesting sector for lightweight PV as of now. And for that, we calculated that lightweight PV has a potential of over 85 gigawatts between commercial and industrial buildings, with Spain, Germany, the Netherlands, Italy, and France leading the countries in terms of potential. And some key drivers for lightweight PV is, first of all, and obviously, structural limitations in construction, so low load-bearing roofs, also snow loads and strict building codes, maturing rooftop PV markets, because if all the rooftops which are easy to install PV on are already have already PV on them, installers will need to look into those roofs that are structurally constrained or more hard to get to. Also NZIA, because some of warehouses or industrial buildings may need to have PV on, and also the practical installation of it, because some of lightweight modules, you can just stick them onto the roof, onto the bitumen, and you're good. It's way easier than having to install a heavy module on top of a roof. Finally, some general conclusions. So first, IPV presents a diverse and growing opportunity across Europe's building, infrastructure, agricultural, and mobility sectors. And BIPV remains the most established IPV market as of now, with many European manufacturers as well. And it will continue to grow consistently, even beyond 2050. PVMB and VIPV will remain as niche markets, even if they have continuous growth. Carport PV holds a massive potential, and it has synergies. It has fantastic synergies with the mobility sector, especially for the commercial applications. AgriPV has by far the biggest market potential out of all the segments we have looked into, but it's still very sensitive to regulation. And well, regulatory frameworks and policy support remain the decisive enablers for all of these IPV applications or advanced modules that we have just discussed. Technological maturity and integration feasibility are key into transforming the potential that we have talked into actual market reality by retaining their dual purpose nature across all stages, across their lifetime. Together, these active applications could deliver hundreds of gigawatts by 2050, contributing meaningfully to Europe's decarbonization goals, as well as optimizing land use. Thank you very much. Now I give this to you if you have any questions.
Thanks a lot, Juan. So, I have a few questions. Probably I will ask my questions, and if there are any in the chat box, please answer there. So, it's interesting you said that the sound barrier is really having a lot of potential, noise barrier, so 400 gigawatt. And you mentioned cost as one of the barrier, if I understand it correctly, for its large scale implementation. But PVs right now is at its lowest cost. So what are the other materials or other components that are making expensive? And then are there also any policy related barriers or regulatory related barriers for these applications? Because just a few minutes ago Hamid showed you, like, there is a plastic fence which costs 99 euros and module costs only 69 or 79 euros. So I think the price of the PV component is coming down. So what else, if we are looking at the cost, what else has to come down for, I took the noise barrier as an example, but in your general understanding, what else has to come down in order to accelerate the deployment of this? And
yeah, and that's a great question. Thank you. And you're right. The solar component part is not the main cost of it, but keeping the dual functionality of it, that's what drives the cost higher. Because its purpose, it's not to generate electricity. Its main focus is still sound protection, and to have the synergy or the combination of both sound protection and electricity generation, that creates complications, not only on the initial fabrication of the module, initial production of the component, but also maintenance. So those are the biggest, and not only for PV. I know you took that as an example, but also, for example, for vehicle integrated PV. That is also one of the reasons.
Okay. And so one more question what I have is, you might have looked at the potential, but do you see anything lacking in all these integrated or, non-traditional applications? So do you see that some growth or some development from the PV side of these components can accelerate this growth, or do you see any material related limitations all coming? So when I'm talking, I'm representing the PV side of it. So do you see anything, probably if this is here and if it goes to this, it could fly. So do you see something interesting in that area from PV side?
Yeah, I think it depends on, we cannot generalize into all IPV applications. For example, if we look into BIPV, yes, obviously better efficiencies or better technologies or better fire resistance, those are all welcome, those are all better. But the main driver really for BIPV that we see is aesthetics, not necessarily electricity generation. But that is not the same case for agriPV, for example, where you want to maximize or optimize land use for electricity generation, but also crops and also fields. So yes, of course, and like we just saw in the previous presentation with about agriPV, about the specific Terra module, those innovations are always welcome and are great for certain sectors. But we cannot just look at IPV or integrated PV as a whole. We need to focus on each individual application. And even inside the segment of agri-PV, you have vertical PV, you have warehouses. You need to look really into what you're trying to focus on.
Okay. Thanks a lot. So this was very insightful. Thanks a lot for your presentation. And if there are any more questions in the chat box, please enjoy our conference while answering these questions.
Thank you very much.
Thank you.